Good evening, everyone. I'm pleased to welcome you at the Data Science webinar, the traditional event in the University of Tartu in the Institute of Computer Science. Today's event is about explainability and governance of artificial intelligence. My name is Mikhail Popkov. I'm a junior research fellow in bioinformatics in the University of Tartu. And today I will be moderating this seminar, meaning that I will be introducing the participants, leading the discussion, and reading your questions from the chat. So today we have 4 speakers. 2 speakers represent the academic part, academic view on the problem. They are namely Meelis Kull, the associate professor in the University of Tartu, and Radwa El Shawi, who is also an associate professor in the University of Tartu in big data. And the last 2 speakers are from the industry, from the company called Vagel. And first of them is Luca Traverso, who is a data scientist in the Vagel, leading the Fincrime development. And the other speaker is Vagel, who is also a data scientist and who will be talking about explaining machine learning models in regulated environments. So the time frame is like that. We will have 20 minutes for each talk. And then you will have an opportunity to ask questions in the special section. So at the bottom of your screen, you have 2 icons. One of them is chat. You don't use that. You use the other one with 2 speech bubbles, which is called Q&A. So in Q&A, you can open the question and I will see it. And then I will read the most upvoted questions or whatever questions I like, because I'm the moderator from the Q&A session. Also, you can upvote the questions of other people if you would like them to pop up and be answered. So feel free to use that. You can do it either publicly or anonymously, so whatever way you feel comfortable. And okay, we already have 89 participants in the room. That's great. And maybe we can start. And first of all, I can start the discussion by introducing the first speaker of today, Meelis Kull. So Meelis is an associate professor in machine learning in the University of Tartu since 2017. He's a very renowned machine learning researcher and lecturer, and a lot of students, more than 1,000 students, have taken Meelis's courses. So probably most of you already knew who Meelis is. And the research that Meelis leads is developing machine learning methods which deliver predictions and well-calibrated self-assessments. So Meelis, the floor is yours. You're welcome to share. And the topic of Meelis's talk would be about understanding the decisions of an AI system.
Thank you. Hi, everyone. My name is Meelis Kull. Very happy to open up this nice event about machine learning and the side of explainability, governance, things that maybe we teach a bit less actually often in the universities when teaching machine learning, but these are very important aspects. I'm not doing research myself on explainability. I'm working more on uncertainty, which is kind of related, but not exactly the same thing. I would like to start with a kind of motivating why we even need explanations. So artificial intelligence is a tool that gets smarter gradually. We have been using it for many purposes, and gradually, basically, it has become a co-worker in many of the tasks that we need to apply it in. So it's rather a collaboration than us using it as a tool sometimes. And so this means that we also need to start to think about, and have for a while already have been thinking about, how to try to understand what AI is doing. So, but still, why? Why do we need to understand what the AI system does? If it does its job well, why not just trust it and all is fine? Why do we need to understand our coworkers? And one reason for that is errors, unfortunately. So that's the negative reason, so to say. And that's kind of the same as with an AI system. So it is possible that this AI system makes errors sometimes. So, and if we understand, maybe we can actually prevent those errors in the first place. Or if they do happen, we can maybe mitigate the effect of those errors. Or even if not that, at least in retrospect, we can try to understand what went wrong. Also from the positive side, it's worth understanding sometimes the AI, because the AI can also be smarter than us in some aspects, and we can actually learn from the AI. So whenever it performs surprisingly well, we maybe better try to understand how come. And an example where maybe a bank is applying an AI system to be more efficient in going through the loan applications and making decisions about them. So maybe the AI makes preliminary decisions and then the human can override those. Or maybe sometimes also when it seems that there is not enough information, and that's why maybe the AI system was not sure about its prediction, then it's possible to seek for further information. So basically that's the why side. But now, who needs to understand? And there are multiple parties that do need to understand. So one reason why a lot of explainability work is done is for the regulatory bodies. So there are laws and regulations, just like GDPR, which basically require that people who are affected by the decisions need to be able to request explanations. So that's one use case. Another kind of related, but also different, is that maybe auditors who are checking whether companies who use AI systems for making decisions about people, whether these are AI systems that are fair and that do not discriminate, do not, for example, take race into account, even if not directly, then not indirectly, because it can happen that other information about the individual can reveal some of those sensitive features that we don't want to be taking into account. Then it could be decision makers who maybe business leader or someone who's operating some kind of a system that involves AI as one component. So those people need to use the decisions that the AI comes up with, but then also to be aware of the uncertainty that these models have, to understand why in a particular situation the AI has made its decision or suggestion, and then knows whether to trust or not. It can also be for AI developers who want to make the AI better. So if they understand better what kinds of mistakes the AI is making, that also helps in improving and kind of finding ways around these errors. maybe gather more data to train better AI models, so then avoid these errors in the future. It can also be that there are co-workers of AI, any other people around the place where the AI is being used, and so they might notice some errors if they understand how the AI operates, and so can let someone know, let the developers know, oh, here is a problem. Or maybe they can even learn from AI if AI system is particularly strong one, and even if the human and the AI are solving different tasks, maybe the human can also gain from understanding more of that other domain where AI is operating. And so there are many more. And importantly, so when we're talking about explainability in AI, it is always important which of those use cases we're talking about, because the explanations, the nature of those explanations needs to be different because of the background of the people is different, the skill sets and so on. So we need to know who the explanations are for. And so then there are many application domains, transportation with autonomous vehicles, because we need to understand why things go wrong, when they go wrong. Healthcare, because the doctors are finally responsive, the ones who are responsible for the treatment decisions. So they can use help from AI, but they need to understand enough to be able to trust and be responsible. Finance, which you will surely hear more about in the industry speakers talks. Military, intelligence, pricing decisions in retail, recommendations, social media. So many places where explanations can be important and relevant. So that's kind of the brief intro to understanding AI. Now, let's discuss some of the concepts. So XAI is the typical acronym these days for explainable AI, and there are two terms that are sometimes used as synonyms, but there can be differences. One is interpretability and the other one is explainability. Interpretability is more like a property of this AI algorithm or model, so that we can kind of understand the way that it operates. So perhaps decision trees are algorithms where we kind of know that how to read out what the prediction will be. So maybe they are interpretable as such already. But then explainable AI is not only about the system itself, but also the interface, how humans understand these decisions of the AI system. So because it's not about maybe getting a PDF file with an explanation necessarily, it can also be an interactive process sometimes. So human gets some information and then can request for more information to understand even better. So explainable AI kind of covers a wider term that covers all of this. Now, so where's the hard part? Isn't it just kind of something that we take this machine learning model, understand it? Why can't we? But note that even us as humans, it's hard to understand each other. So it's even harder to understand than someone who is having a different cultural background and different skill set. And AI is just an extreme of that. Very different culture and very different skill set. And when trying to understand the AI, it's good if the person already has some knowledge about the culture of AI, what can and skill set of AI, what can or cannot it do currently, and these particular methods then that are being used. A big challenge in this explainability is the trade-off between whether the explanation is kind of more understandable or more accurate or more faithful to how the decision was actually made. So let me try to illustrate with an example. So suppose a personal credit risk decision, or how whether basically as a way to decide whether to give out a loan or not, maybe it's a decision tree. And so here is a big tree. Every node is testing some feature, and then once you have kind of the model has checked the values of features, it comes at the leaf with a decision. Now, if you want to explain it, I mean, the tree itself is an explanation, but it's very big sometimes. I mean, this is a small one, it can get very much bigger. So maybe we want to just cut it a lot smaller. So zooming in, something like checking balance, installment plan, yes or no, months loan duration, credit history, kind of properties relating to this personal credit risk. So these features are kind of human interpretable. So we see how at least the model starts to make the decision. Maybe we cannot see the code here, but it's kind of a simplified explanation of the whole model. But of course, this is now much less accurate than the whole tree. So we have, because of the trade-off, we have worse model, but then at least more explainable here. And this is less explainable but more accurate. So basically, decision trees can go big. That's one challenge in explainability. But then often ensembles of decision trees are used, either in random forests or some gradient boosted trees. So there are then hundreds of those trees. So how do you kind of understand the decision of that set of trees? Even worse, kind of, if you take neural networks, the decision process itself is a huge computation, and it can, depending on the size of the net, it can be billions of computations that go on. And so how do you even start to understand that? Now, kind of, what are the principles? So this is just one source, one view of explainability principles. There are many more. So, but this one emphasizes that first of all, there needs to be an explanation. AI system needs to be able to provide this evidence or support or reasoning. It needs to be meaningful to those users who need it. And as I explained, there are many different use cases. So depending on the use case, it needs to be meaningful. And then it needs to be accurate. And this relates to the trade-off between explainability and accuracy. And also then the fourth principle highlighted here is the limits of knowledge. So AI system should also then identify the cases where it is not designed to work, where it can fail, where it shouldn't be trusted. And then that needs to be taken into account. This is one of the kind of clear weaknesses of current AI systems, that it's really hard to clearly express what the knowledge limits are. If your kind of new data on which you apply the system come from exactly the same pool from which the training set was gathered, then you're quite well off. Probably it works fine, but at the moment, but then time passes and the training set may be statically in a year or two ago gathered, and now things are different. So you no longer have the confidence that the model really is within the knowledge limits still. Now, getting a bit towards explanations, the kinds of explanations. So one is global explanation. So the model as a whole should be then explained. So basically, try to understand how the AI system makes its decisions and what information does it use or does not use. So maybe some of the features are not in the tree even, so it doesn't need that information. And then also what information contributes more to the decisions. In contrast, local explanations are not about the whole model. They are particularly about a specific instance. And it's kind of retrospective explanation to why did the model make this particular decision, what information did it use or not, and also then what turned out to be more important for this decision to come out as it came. So this is kind of one path within a decision tree in case of decision tree models. Properties of XAI, so the model itself can be transparent, so you can kind of understand it, or it could be opaque, but it's a scale, kind of continuum scale. So some models are less or more transparent. Now the explainability methods could be more like model agnostic, so they could work on any models, or they could be specifically working only for neural nets, for example. As I said, explanations could be global or local. And now I would also like to briefly talk about some methods. So first set, kind of the most general ones are local model agnostic approaches. So basically they work for any models and they are local. So one particular instance can be explained why this decision was made. One way is counterfactual. So basically so currently I didn't get the loan. What should have been different so that I could have got the loan? And so the counterfactual could say, oh, if only you had actually earnings of 10% more, you could have got the loan. Feature importances are talking about each of the features or properties about the instance and highlighting them, which contributed particularly to this decision and how important different features were. And then there could be surrogate models. So there is this big model that was actually used to make the decisions. And this is hard to explain because it's so complicated, but for this particular instance, we can take a small surrounding around it and then come up with a more interpretable model. So maybe a decision tree or maybe a linear model, which is just overall, it's far from being the same as a big complex model. But locally, near this instance, on similar instances like this, it is quite a faithful representation of what the big model does. And so line is one example of such kind of methods. So here is an example where based on features like weight and age and some symptoms, it suggests this is a flu, and then it can be explained to the, let's say, doctor who makes the decision. By highlighting locally people similar to this person, the model uses these kind of weights to make its decision, and sneeze and headache positively contributing, no fatigue negatively, and that's how the results came. Then very general approach is Shapley values originating from game theory, and this about originally about K partners contributing to some enterprise, working together, getting some profit from that. But then how should that profit be distributed? So suppose there are two partners, one alone would get 1 million euros from this enterprise, another alone, if would work alone, would get 2 million, but jointly there is a kind of synergy and they would get 4 million. But how should that 4 million now be split between the two people? And basically Shapley values is very principled, derived from axioms way to calculate, and basically skipping the details. It's saying that in this case it should be 1.5 to one person and 2.5 to another person. And for machine learning particularly, it's about features instead of those partners, and then decision is the profit. And so you can answer the question of how much of the decision should be attributed to each of those features. And so this is really kind of general method. And very finally, very briefly about deep nets and their explanations. So the problems with typical explanation methods is that, I mean, here the pixels are the features. So every single pixel is really not affecting much of the decision. But somehow jointly they do. So how to attribute this to different parts of the image? I'll skip a bit of kind of the global explanations of deep nets, so you can try to understand what the units do, what are they most activated by, what kind of patterns, or but then if you locally want to explain why did the neural net predict a boat, then you can basically ask which by changing making small changes to pixels, how much that would affect the prediction, and that can be calculated using gradients. There are kind of meaningful results. So here is an octopus misclassified as an eel with different methods. So one method that gives the wrong answer, but then different explanation methods. And so vanilla gradient tries to highlight what pixels contributed more, not doing a very good job. And then there are some other methods that start to at least highlight the right kind of pixels, but then that really doesn't justify why it's not an octopus, but rather an eel, according to the model. And so basically that summarizes this brief introduction to explainable AI. I hope this helps the following presenters as well, not having to kind of talk so much about the basics. But any questions, welcome.
Thank you very much for the presentation. Yes, there are some questions in the chat, so we'll probably have time for one of them. I guess it's rather general and maybe answered in the following presentations. But basically, the question is, how much are we there already? So, are there any existing systems like in production that satisfy like all four principles of explainable AI?
I think we're definitely not there yet. I mean, partly it is a problem which kind of gets worse and worse as the models get more complicated. So we maybe get better at explaining the simpler ones, but then yet another more complicated one emerges. So there are definitely tools that kind of provide explanations in form of kind of how important one feature is and another feature, how much different pixels contributed to the decisions in case of vision. So tools are there, but they are particularly limited in terms of how much you can even trust the explanation itself, because the models are complicated often, and there is this trade-off of explainability and accuracy of the explanation.
So the general trend is the more accurate the model is, the less we are able to explain it, right?
Yes, the smarter the person is, the harder it's to understand how that person has come to that decision. That's unfortunately so.
Okay. Thank you very much, Meelis. I think we can move on to the next speaker. The next speaker today is Radwa El Shawi, who is an associate professor of the big data in the University of Tartu. Radwa's research focuses on the automated machine learning and explainable artificial intelligence. So, Radwa, please, the floor is yours.
Thank you so much. Hello, everyone. At the beginning, I would like to thank you so much for having me today. Today, I'm going to talk about a specific category of explanations technique called concept-based explanation techniques. We'll start my presentation with a definition for machine learning interpretability. So one way to define machine learning interpretability is the degree to which an observer can understand the cause of a decision. So according to Miller, as you can see in the definition, it's very user dependent. So for example, a good explanation for you may not be a good explanation for me. It's very subjective. And there's no also wide agreement upon a specific format for the explanation. So different interpretability techniques provide explanations in different formats. Some of them in terms of feature attribution, as Meelis mentioned, in which they highlight the importance of each of the features used in training the model. Other category of explanation techniques provide explanations in the form of rules. Others provide explanations in the form of influential instances. Like, for example, if I would like to explain why this model has predicted a specific patient as a high risk of mortality, the explanation comes in the format of different or a number of instances from the training data that contribute to that prediction. Another also category of explanation techniques focus on explaining instances or models in counterfactual explanation. Another also category provide explanation in the form of high-level human understandable concept. And this will be the main focus of today's presentation. Sometimes the low-level features used in training the model, sometimes they are not meaningful by their own. And in order to provide explanation that is more human-centric, we need to take these low-level features and transfer them into high-level concepts and provide the explanation in terms of these concepts rather than the features used in training. So the topic of machine learning interpretability received great attention, especially after the General Data Protection Regulation imposed in 2018 that asked any decision taken automatically to be explained. Since then, lots of techniques actually appeared that addressed the interpretability on the global level and on the local level as well. But we're still very far away from our destination. We're still very far away from having a technique that can provide users with, or that help users to take more and better decisions. So machine learning interpretability is very challenging, mainly because of the evaluation. So if you compare, for example, machine learning interpretability to supervised learning, you can see how challenging it is. So in supervised learning, you have, so assume that you would like to train a model to predict something. You have something to measure the goodness of the model. You have a metric. So I can measure the performance of the model using accuracy, area under the curve. I have something to measure. But in machine learning, interpretability is very difficult because it's very subjective. So we cannot all agree on an explanation, or we cannot all agree that we can comprehend this explanation. And that's why it's very challenging. And the approach that I'm going to talk about today is called concept-based interpretability, which is more human-centric approach that hopefully can take up a step forward to reach a good explanation that really can help decision makers. For the rest of the presentation, I'm going to assume that we have data and we have trained model and a specific category of models. Here we are going to focus on neural networks, and we have access to this data and access to the model as well. So the techniques that I'm going to talk about today are not model agnostic, are model specific, only can explain a specific category of models. And once again, we assume that we have access to the training data used in training these models and also the models themselves. So if we have a look on these two images has, so the first image here on the left, this image has been predicted as a cache machine. And if we have a look on one of possible techniques for explaining this image, one of the techniques is mainly here, we use the grade CAM. It's still under the category of feature attribution, in which we are trying to get the importance of each pixel in the image. So as you can see from the explanation, it's not meaningful at all. So if I have a look here, it's very hard to know why this image has been predicted as a cache machine. So I can't answer a question like, for example, which pixels are more important, the pixel of the person or the pixel of the cache machine? It's very hard to tell. And again, here also, if you have a look on this image has been predicted as a sliding door. But if you have a look on the explanation provided from GreatCam, it's very hard also to tell which concept is more important, or which is more important in general, the paper or the sliding door, which pixels are more important to the prediction. Again, it's very hard to tell. So really, would it be more useful if we can quantify the importance of user-defined concepts rather than pixels? Would it be more meaningful? This is actually will take us to the first technique here from the category of the concept-based interpretability techniques. This technique is called the TCAV, testing with concept activation vectors. This is a great work that has been done by Google Brain. And in this work, they are trying to find the quantitative explanation. They are trying to answer a question like how much a particular concept was important to the prediction of a specific class. So, for example, once again, we have the same assumption is that we have the same assumption that we have here a trained model, and we have also access to the training data. And we, as a user, I need to identify a concept that I would like to test its importance. So as a user here, I choose to quantify, or I choose to ask about the importance of a specific concept stripes to the prediction of class zebra, for example. And what's the TCAV output? The TCAV output is a score that tells you how important this concept to the prediction of this zebra image. So let us now have a look and see how TCAV is calculated. So the first step in order to calculate the TCAV is to calculate something called a concept activation vector. So, and in order to calculate this concept activation vector, you need at the beginning to identify the concept that you would like to study or to test its importance. Here in this example, the concept is stripes. And you need to have a data set. And this data set has some positive examples for the concept and some negative examples for the concept. And this is the network. This is the black box model that we are trying actually to explain the prediction. And what we are going to do is that we are going to learn a model that can discriminate between the positive examples and the negative examples. As you can see here, this is a linear model that try to discriminate between the positive examples of the concepts and the negative examples. And then the CAV vector is actually a vector that is perpendicular to the decision boundary here. This is to the direction or toward the concept examples. So this is actually called the CAV vector. And what we are going to do is that we are going to take each image in this class, the class zebra that we would like to test the importance of concept stripes to, and then we are going to calculate the sensitivity of each prediction to that concept. And that's give us indication about how important this concept to each image in the class. And at the end, in order to get the final score of how important the concept to the whole class, this is the TCAV formula. Simply, we are going to find the ratio between instances that have positive sensitivity to the total number of instances in the class. This gives us indication about how important that concept to the class. The technique actually is very powerful, very interesting, very human-centric, very flexible in the sense also that it allows the user to test any concept of his choice. But the technique also has some limitations. So for example, as a user, I may not know the right set of concepts to query or the important concepts to query. And even if I have, maybe I don't have enough examples for the concept in order to learn. And this is mainly the main limitations of this technique. And the question now, can we do better? And wouldn't it be actually more useful if we can quantify the importance of automatically extracted concepts rather than user-defined concepts? that actually will take us to the next technique, which is called automated concept-based decision tree explanations for convolution neural network, ECDT. This work is a joint work with Professor Sharif Sakr and Yusuf Sharif. And as I mentioned, in this technique, we are trying to solve the limitations of the TCAF technique, in which we are trying to extract the concepts automatically from the data. So instead of asking the user to identify or asking the user to identify a concept to test and also provide training data for this concept, we are going to extract the concepts directly from the training data. And then again, we are going to provide the explanation in terms of these concepts. And also, in addition, we are going to provide a counterfactual explanation, which is in the form of what are the minimum concepts that could be changed in the instance that you are trying to explain to change its prediction. Like, for example, if this image has been predicted as a post image, so the explanation come in the form that the reason for that prediction is that it's that this image has concept mountain and has concept C. But if we don't have concept C, this image would be predicted as highway. This is the two forms of explanations we provide. So we answer the question why, and also we answer the question why not. So let us have a look on the technique and how it works. The technique mainly consists of three main stages. The first stage is the concept extraction stage, in which we are trying to extract the concepts automatically from the data. The idea is very simple. This is the image that we are trying to explain. At the beginning, we are going to retrieve the most similar images to this image from the training data. And the next step is that we are going to apply a semantic segmentation. And the next step is that we are going to cluster these segments. And by clustering these segments, we are going to have a set of equivalent to the positive examples in the TCAF. So for example, by clustering these segments, we can obtain somehow meaningful concepts. Like, for example, this cluster is for concept sofa, this cluster is for concept bed, this cluster is for concept wall, something like that. Some meaningful concepts automatically extracted from the data. So the next step or the next stage in the technique is that we are going to learn interpretable concept detectors. What does that mean? We would like actually, now we have the positive examples, but we would like actually to have a model that can tell me whether this concept exists in this image or not. This is a model called concept detector. It's simply a linear model that for each concept, we are going to do the following. We take the positive examples from the concept, from these steps. So for example, if I would like to train a concept detector for concept sofa, so I'm going to take all positive examples, which is the segments in this cluster, and I'm going to take some negative examples, randomly selected from the different clusters, and then I'm going to build a linear model that try to detect the presence or absence of the concept in any image. I'm going to repeat the process for each of the concepts I have in my for all the automatically extracted concept. And the next step is that I'm going for each of the images that I retrieved, the k similar images to the image that I'm trying to explain. I'm going to take each of these images and take it through the different concept detectors and check the presence or absence of each concept in this image. And then I'm going to build a feature vector like this one. So for example, 0 means that the first concept does not actually present in the first in this image. 1 means that the second concept exists in this image, and so on. And then I'm going to take this representation and use it to build on the top of it a decision tree. And now the decision tree actually relies on not the low-level features used in the training, but the high-level concepts. And I'm using these concepts to explain the prediction. As you can see, I have a decision tree, and using this decision tree, I can explain provide explanation for why and also for why not a particular class. So, for example, once again, if we consider the same example from the previous slide for the image that has been predicted as a coast image, this is the explanation. It's because it has a mountain, it has a sea, and this is the counterfactual factual when I can, what is the minimum number of changes that can happen in this explanation to change the prediction? It would be the absence of the concept C. So the idea of the technique is quite simple, but let us have a look on how we evaluated this technique. Mainly, most of the interpretability techniques relies on human-based evaluation. So we relied in the evaluation on some human-based evaluations. And in order to measure the meaningfulness of the concepts we extracted, we present the participants two groups of images. The first group on the right represent images from a particular concept, and the images on the left represent images taken from a specific cluster, and the images to the right are randomly selected from the different clusters. And then we ask the user what group of images is more meaningful to you. And in order to measure the quality of or the importance of the concepts we used in the explanation, we also rely on human-based experiments in which we provide users with the image and the prediction. So for example, this image has been predicted as a street. So we provide the image along with the prediction and some images here, 4 images in which one of them is the most important one returned from our technique. And the other 3 ones are randomly selected from the different clusters. And again, we ask them which one is the most one, or what do you think is the most important concept that contribute to the prediction of this image as a street. This is simply how we evaluated the technique, but the technique still have some limitations. It's not fully automatically. We still have some limitations in the way we cluster the concepts. Not all the time we can have meaningful clusters. In sometimes the clusters are not meaningful, and sometimes we need to merge some clusters. So the process is not fully automated. And also another important actually limitation of the technique is that now we go from fully manually to fully automated, but we need something in between. We need something that incorporates user feedback into forming these concepts. So I need the user to give me feedback on the automatically extracted concept and integrating or incorporating these feedback in the learning process in order to provide better explanation. So before I conclude my presentation today, I will highlight some of the challenges that we have in this area. Most of the framework have the assumption that there is a single explanation that can fit all, and this is totally not realistic assumptions. There is no single explanation that can fit all. So for example, if we have a model for predicting the risk of diabetes, for example, the risk of mortality, and this model is used by physicians and also used by patients, the explanation that is provided to users as to patients should be different from the one provided to physicians. We need to take into account the user when providing the explanation. So we need to work more on customizing the explanation according to the group of users using the explanation technique. The second important issue in the area is the evaluation. There is no agreement upon evaluation protocol for comparing the different frameworks. And this is actually why it's very difficult to say, for example, which interpretability technique is better, X or Y. Or if I have a data set with this characteristic and a task with this characteristic, which one should I use? Nobody actually can answer this question because we have a problem mainly in the evaluation. As I mentioned, we need also to integrate the human feedback into forming the forming the explanation to provide better explanations that hopefully will be or will help decision makers to take better decisions. Thank you so much, and I'm ready to take your questions. Thank you.
Thank you very much for the presentation. We have a couple of questions in the chat concerning the automated concept extraction step. So am I correct that these concepts to extract, you use semantic segmentation model for this purpose, right?
Yes, we apply semantic segmentation technique to extract it from all the training examples, and then we cluster them to form the concepts. Okay, so this means that like the space of possible concepts, it's somehow restricted to the class space of this model, right? Yes. Okay, so we cannot, like, I don't know, guess an extra concept for the data set. Okay. And another question concerning the same topic about the concept extraction. Can we actually explain this step? So which steps? This step of semantic segmentation. So is this we apply a deep lab, I think V3. We apply a specific semantic segmentation technique. We tried different ones, and this is the one actually that provide us with more meaningful concepts upon inspection. Okay, okay. Thank you very much. Thanks a lot for the presentation. I think we can actually consider another question from the chat. We have time for that. So there was a question about so if some of the features, let's say, what some of the concepts are not interpretable per se. So, for example, the semantic segmentation model failed for some reason. So, what would happen on the next step? That's what I said. This is one of the limitations of the technique, that we need to inspect the clusters manually, because sometimes we need to merge actually some clusters. Some clusters sometimes be redundant. Some of them be, for example, not meaningful. Sometimes we end up having a clusters of 2 segments. So we need to inspect the clusters and remove the clusters that doesn't make sense. So there is here some, it's not fully automated, as I mentioned. We need actually here to inspect the clusters to make sure at the end that the explanation using these clusters will be meaningful. Okay, so there is some human involved in this step. Yes, okay. yes, there is. It's not completely automated. And the next step is that what we are trying to do is we are trying to integrate the user feedback so we hopefully can learn better concepts. And another question from me perhaps is that can we possibly extend this technique of concept extraction to other domains, like, for example, videos, or if we talking about like texts, would that be possible? For video, I'm not sure, but for example, for the tabular data, for example, there is a technique that is trying to incorporate based also in concepts, but we are trying to incorporate the user feedback also. For text data, I think yes, but the problem is how you are going to define the concepts. It's not that straightforward, so the automation is not that straightforward. Okay, okay, understood. Thank you very much. It was really insightful. I think we can move on to the next presenter meanwhile. So Luca, could you please share the screen? And yeah, please welcome Luca Traverso, who is gonna present about building a robust and defensible machine learning systems in crime. I suppose it's about financial crimes. And Luca is a scientist in WISE with many years of experience working with the data in various industries and countries. And for the last 4 years, Luca was working as a data scientist and for the fraud prevention and detection domain. And now Luca oversees machine learning development and the whole Fincrime department in WISE. So Luca, you're welcome, and the stage is yours.
Thanks, Mikhail. I had the presentation at the bottom, so you see it all, but nice to be here. So actually, my presentation is a little bit more practical than the latest one, but it is great to see that there is sort of this high level of research going on into making machine learning models interpretable. And so like my presentation looks a little bit more at the more sort of generic scope of model governance. And it kind of links quite a bit with what Meelis said at the beginning, right? We may be ending up in a situation where we are able to interpret or explain our models, but these models have been sort of static for years, and you are not aware of what has been going on in the training set, etc. So that's a pretty bad situation to be in, and this presentation exactly sort of wants to give you a concrete example of how we go about avoiding such a situation. And so it's all about building robust and defensible machine learning systems with a particular focus on the Fincrime domain. And interpretability is just one aspect of this. It's not the main aspect. So I would like to actually, the first part of my presentation would be sort of introducing what the problem is, and also sort of tell you why do we use machine learning? Why do we need to use machine learning to solve this problem? So in my team, which is sort of looks after sort of preventing and detecting sort of bad actors that may come to our platform or any actually financial institution. Our objective is obviously to leave these sort of bad actors out of the system, or if they are smart enough and they are able to sort of interact with the platform, to detect them at that point. So what happens is that unfortunately, when we try to detect the bad actors, we also impact a small amount of good customers. So this is what make up our false positive component. And of course, the bad actors is our true positive component. In the detection systems. And so like the false positives and the true positives make up what is our backlog. This backlog effectively needs to be reviewed. It's very often represents a certain number of alerts or a certain numbers of manual manual reviews that needs to occur. What we have seen over the years is that, particularly in fast-growing companies such as Wise, what happens is that as the company grows in terms of volume, because sort of we grow horizontally as well as vertically, right? Sort of enhancing our product offering and also vertically having more customers. What happens is that with the sort of static techniques, we have a kind of a backlog that grows with the volume. So this is a pretty difficult situation to be in, because you want to grow, but at the same time, the alerts that the system generates grows as well. So that means that obviously it's a very difficult situation to be in, because that generates a lot of queues and a lot of waiting, right? What we have seen over the years is that with machine learning, we are able actually to stabilize the growth of that backlog, actually even making it so that it trends down, although we are still experiencing a lot of growth with the company. This is a very good situation to be in, right? Because that means that day on day, the number of customers and that sort of you impact and they make up the part, sort of your backlog, is effectively constant. And that means in practical terms means that differently from a backlog that grows over time with your volume, and therefore you have an operational team that grows with that as well, because you are always sort of in the back foot and having to catch up and having to sort of review those alerts that are generated. We see that with machine learning, as we have this constant sort of backlog creation, we have also a very nice stabilization of our operational team growth. This is a very ideal and good situation to be in, and this is what we have sort of seen. And a lot of this, it is thanks to sort of machine learning techniques that have been developed over the last decade. It's also true that if you look at the time to get to the alerts, right? So if you have these queues that grow over time, it means that you get to those alerts in quite significant amount of time. That means that potentially bad actors sits in queues for quite a bit of time, and you do not know what they are doing and how they are behaving, right? Depending on what system you have. And so actually your risk grows with your financial risk actually grows. You are generating more alerts. It doesn't mean that you have more coverage. It's quite the opposite, because you are increasing the time that you get to those alerts. So you are exposing yourself to higher risk. The same actually with the customer negative impact. So like the good customers also end up in those queues, and therefore they are negatively impacted. So what we are seeing is that with machine learning system, we are able to stabilize our backlog creation, which is really, really good, and reduce our risk exposure, which is really what we should aim for, and also have less negative impact to our good customers, in the sense that in case of false positives, they stay in those queues for a limited amount of time. What we have seen, though, as we interact more and more with auditors, regulators, etc., is that if you use a machine learning system, what you are also expected to is to have a robust and defensible machine learning system. And by robust, I mean that a system that it is able to adapt to sort of fast changing conditions. And defensible is a system that can be understood easily, and it is credible to third party. And by those third party, I mean regulators, auditors, but even your sort of your colleagues in other teams. So how do we go about generating such systems? So in our experience, we have seen that we need to have at least 4 components in place. So we need to have good logic for feature creation and good labeling of cases. We have seen that it's important to have a system that sort of automatic or semi-automatically is able to keep your models up to date through model retraining. So to avoid exactly the same situation that was mentioned earlier. And also important is, which is kind of a derived effect of sort of automatic model retraining, is that we have a closed loop learning, right? We have the system that is always up to date, and therefore it can continuously learn from what our operational teams sort of decisions are. All of these actually really nice fits within the whole governance of models. So if you have good features logic, if you have good systems for model update, you have in place a sort of solid foundation for model governance. And then, of course, model interpretability comes as, I would say, the last step. But that doesn't mean that it is less important. It's fundamental. It's important, but it cannot exist on its own, especially if you are lacking on all the other things that I mentioned before. So let's start with the feature creation and labeling. So we all know what is a feature, right? Particularly in sort of machine learning systems using sort of classifications as algorithms under the hood. We want to represent some kind of observed behavior in a numerical format. That is what is a feature for us. Now, I guess for me, and I am a huge advocate of this, is that sort of our feature creation and feature logic always start from our expert, and our expert are our sort of operational team. So it's the team that actually review the cases that the machine detects, and they spend time sort of investigating those cases. So they are sort of the treasure box of knowledge for us. And a thing that we have put in place is that we have these strong collaborations between data scientists and our operational team. This is like a strong synergy between these two groups of peoples. What that makes is that helps us with defending our models, because the features we create, they don't come out from some magic, right? But they come up from a thought-through process, and they come out from this synergy between data scientists and our operational team. So in my opinion, if your features that you are using in your models can be explained, then the model results that come out at the other end are also potentially easily explained and interpreted. Also, so that is for features, of course, and then the other component in the machine learning models that we build is the labels, right? So we have features, we have labels, and then we have an algorithms that sort of try to differentiate the classes. So the labels is basically our classes, right? And again, at the core is our operational team. Our operational team review cases and provides us with the labels. What we need to put in place, and what we see that auditors ask us to have in place, is a system so that these decisions made by our operational teams are tracked and sort of stored in tables, right? Once you have those stored, then you can use them to train your models, and we will see that later on. So over the years, we have built a whole bunch of toolings, right? Investigation toolings, toolings that can support our operational team in their work, and helps them with sort of labeling cases so that this can be used later on by the machine learning system. But let's get to the core, right, of our sort of governance process, or what makes the foundation of our governance process, which is really our system of training, deploying models. Like sort of in a schematic way, it looks like this. It has many components, right? And sort of on the right-hand side, I also put a few of the sort of tech stack that we use, but it's not really limited to those tools. We sort of very like to experiment and introduce new toolings and new technologies. And so I would like us to spend a few minutes on this, right, starting from the first part. So once we have labels and features, right, we can train our models. So one key point here is that our training sets, our data set needs to be up to date at all times. Like I sort of write here at least daily, but actually even more frequently, right? Like you want to have always training sets ready to be used. Like especially with Fincrime, you cannot be on the back foot, that you have to wait for your data set, your training sets to be generated. That's already too late for you. So the idea here is that at all times we have fresh data sets to be used. And then of course, once you have these fresh data sets, you can actually train your models. And to which we also attach like a level of model tuning. And very important actually, and that makes up the sort of the basis of a good model governance, is that whatever you do with model training, whatever you do with model tuning, you need to log it. You need to log it, and it needs to be logged in a safe way, so that actually 6 months down the track, you can go back to whatever was the model at time T, and you know what was used, you know what parameters were used, you know actually the whole data set that was used at that specific time. So this is really important for example, auditors. One thing that actually comes after that, right, is the ability of testing continuously new models. So that's what we are trying to develop, right? Like almost like think about a system is like in an industry, like a chain that keeps producing models and models ready for testing. So we have sort of semi-automatic testing procedures that allows us to define through sensitivity analysis and like a cost matrix, right? To which we can also include a sort of risk tolerance and risk different risk levels, right? To define the model thresholds. And then, of course, models after testing, they get deployed and they are ready for scoring. So one important things of the scoring part is that we in certain areas of Fincrime, we actually require to have live scoring. So we cannot do sort of offline scoring. That's already too late, right? To act, you need to be able to act when a certain payment is happening. You do not have time to sort of retrospectively look at certain sort of payments or profiles. So what happens? What we do sort of feature engineering and feature gathering live. So there is very complex engineering services that accomplish this. Some very smart people looking at streaming engine and very complex sort of data processing techniques that generate features, and they basically pass these features to the model for model scoring. A very cool thing, of course, is that as these features are gathered and produced, they are also sort of stored and ready to be used for training. And so you can see how the closed loop learning, or the first part of the closed loop learning is established. Of course, model scoring, we need to use that model of output, that prediction. And for that, we sort of use certain thresholds, and then based on the thresholds, we sort of pass certain cases to review to our operational team. And so you can see whatever this decision is taken by the operational team, this is then eventually passed to the system for model auto retraining, right? So the closed loop learning is now complete, and this is refreshed. We have situations where our data set is refreshed very, very frequently, and they are able to pick up the learning that has occurred from our operational team. So when you actually have those things that I have already talked in place, your model governance also comes out of the box in a certain sense. It's already all there, actually, because you have product coverage, in the sense that if you scale horizontally and your product offering grows, you have a very easy system in which you can add models, because the steps of automatizing certain processes is already in place, so you can add more models. Of course, also that also implies a risk typology coverage as well, if you have new typologies of crime developing. So the basis of model governance, based on feedback from auditors, is always that the data needs to be up to date, right? And models need to be updated frequently. And so to not sort of establish that culture of do and forget attitude, right? Believe me, I wrote this before Meelis' talk, and I'm really pleased that he brought up that case of static trainings being sort of unrefreshed for a year or 2 years, right? That doesn't really make any sense, and that's how your model governance, a good model governance, avoid for that situation to happen. Of course, in the model governance, we track all the important model metrics in productions, and there, I guess you can do, you can either frequently retrain your models, or you can actually, based on some kind of quality deterioration, trigger the model retraining. We actually, we are exploring this kind of opportunity as well. But if you don't have that in place, you can sort of cover yourself, just retrain the models frequently. This is actually all that, for example, auditors need to see, actually, that you don't just forget training sets in a hard disk for years. So, of course, one area that we are investing quite a bit of time and efforts is sort of features quality and labels quality sort of monitoring. We are tackling this problem at different levels, not only from a data science perspective, but also from an analytics and from an engineering perspective. So the more monitoring you have of how quality sort of quality checks of your features and labels, the better. So at the end, sort of, we get to the model interpretability, right? So very often I find that it is a little bit misleading, people focusing a lot in the interpretability as something that you must have for your machine learning system. But actually you need to, I would say that more importantly, you have to have all the other things that I mentioned in place before. Then you can actually focus on model interpretability. So model interpretability is good, and at the moment what we have used, and sort of again linking with what Meelis said earlier, we have experiment with Shapley and Lime. We find that Shapley works very nice for local interpretability. That's the kind of interpretability that we look primarily, rather than sort of global interpretability, so that, for example, we have a fraud score of 0.79 or whatever, we can actually break it down into the features that are the main contributors to that fraud score. So what we actually have done and integrated with our tooling is we basically display this breakup of importance. So we tend to not plot every features that we have in the system, but focus on the main ones, the top 10 or something like that. And so we are able to actually plot the features that primarily contribute into pushing the fraud score or whatever risk score high, and the top 10 features that push the sort of risk score down. And this is what comes out of the box using some of these techniques, Shapley or Lime. So, like in terms of where do we need, what are our needs in terms of interpreting the models? I think depending on which Fincrime area, you have different needs. At the moment, for example, if you are in fraud, you have certain needs. If you are in sort of anti-money laundering, you have other needs, right? So, but generally we see that actually explaining, breaking it down by Shapley contributions potentially can work for both cases. Also, what we find is that, and sort of we get together actually quite frequently to look at what are the models for specific cases, for specific predictions, what are the contributors, right, in terms of features. And I do feel really strong about this, actually, that many times, not always, right, there are some edge cases, of course, but we see that many times, if we know what we have in the models, and if we know why a certain feature exists in the model, then we are actually able to explain the outcome or interpret it. I'm not saying that it is always the case, but actually in quite many situations, we are able to see, oh, actually, here is where the machine has seen, here is what the behavior that the machine has detected as anomalous or atypical, or sort of correlating a lot with the fraud that it is present in the training set. So again, emphasizing that actually, if we have this this link between features representing specific patterns or behavior, then actually we make our life easier. Finally, sort of, and to conclude my talk, I think the main challenges that we face is making sure that we have a scaling machine learning infrastructure, right? We don't want to be in a situations where you know, we have sort of growth in volume and our infrastructure is not suitable to take that volume growth. I think that at the moment we do very well, and I think we have all the resources that that needs to be in place. But I guess I'm talking about sort of more for the future, right? What if we if the volume growth is 10x or 100x, right? So this for sure will bring some challenges, and so we need to be prepared for those challenges. And then one thing to sort of link with what Radwa talked is maybe what if we have like, and we do have like models with hundreds of features. A nice thing would be actually to be able to sort of upscale kind of in features group in terms of interpreting the model results. What if groups of features can indeed be grouped together? Then probably that will also help us to interpret more difficult cases, right? So like maybe it also unlocks us the ability with generating some narratives of model decision. That is definitely something we will be looking and hope collaborate also with Radwa to see if there is possibility to achieve that with our models. And then, of course, another challenge that that we are spending a lot of time and efforts, as I mentioned earlier, is to enhance our monitoring for features and labels quality. That is something that it is very important. So this is my presentation, and happy to take some questions at this stage.
Yeah, thanks a lot, Luca. We have time for one quick question about the content of the presentation. So in the beginning, you were talking about the backlog.
Yeah.
Could you please reiterate the backlog of what?
Yeah. Well, yes, like it's maybe a little, so like people call it backlog, people call it queues, etc. All the financial institutions have sort of by regulation, they have they need to put in place a way of monitoring transactions that happens in a financial institution, and therefore whenever sort of something anomalous is detected, that basically needs review. So it basically is a contribution to your queue, right? As you have many of these, then you know, your queues grows. So this is a problem that many financial institutions face. And so I was presenting how in our case we managed to actually bring this to a pretty good control thanks to machine learning.
Okay, thank you very much. I think we should move on to the next presenter on maybe a similar topic, because Ryan Vagel, he also works for WISE in the financial crime department. And currently Ryan is developing machine learning solutions to mitigate high-risk areas, such as, for example, money laundering or terrorism financing or human trafficking, nasty stuff like that, with the anti-money laundering team. So the topic of Ryan's talk would be why did the model decide A? Explaining machine learning models in regulated environments. So Ryan, please, the floor is yours.
Yep. Thank you, Mikhail. Let me share my screen and let's get started with the presentation as well. So, hello, I'm Ryan, and as Mikhail explained, I will be talking about the interpretability of different controls and machine learning, more specifically in highly regulated environments, which WISE is operating in. So, a bit about me. So I have over 2 years of experience in mitigating financial crime. This is in WISE, so first in fraud team and then moving on to the anti-money laundering team, where we not only look at money laundering, but we're also mitigating other high risk scenarios such as human trafficking and terrorism financing. And currently in an aspect where we are introducing machine learning as a control in these highly regulated environments, which has given me a very unique experience in actually managing external stakeholders when it comes to different compliance people, auditors, regulators. So it's a very, very kind of different world, and I think very often is glazed past when it comes to academia or implementing machine learning in the private sector as well. And this also means that we're in the process of managing a shift from something that regulators are very familiar with, so static rules, to something that they are not as familiar with, and maybe in some cases where regulations have actually not really caught up with the private sector, which is machine learning. And it has some additional challenges as well. So we'll mostly be talking about why we need interpretability in the first place, what are glass box and black box models, the interpretability of these different controls, and finally, how to actually present the interpretability or this kind of explanation area, as Meelis brought out, to the different end consumers that we actually see and that we are working with. So you can see that it links with all the previous presentations, and my presentation is kind of a deep dive into one area that Luca touched on, which is models interpretability. So why interpretability? Why invest in it? Why look into it? So what, for example, in Wise, Jack is trying to send money to Chill, right? And for every transfer, we have to monitor the transfer behaviors, right? So if we use a model for it, at the end of the day, the model is going to output, is it suspicious or not suspicious, based on maybe some threshold that we have set, right? And this generates work for our operational agents. So it generates cases, which at the end translates to backlog, which is what Luca explained, and how to actually keep everything scalable. But the use of models also raises some questions, right? So why did the model decide so? Why did it decide that somebody is suspicious rather than not suspicious, or even vice versa? Why are they not suspicious? Maybe they should be. And what would actually happen if we change something about the customer's behavior? So for example, maybe we increase the amount of volume that they're actually sending. What would the model do in that case? What would the model do if an auditor comes to us with a scenario that they know is some kind of financial crime? How well would our model handle that? Why would the model handle it correctly? Why not correctly? And this is very, very important in high risk areas, such as terrorism finance. So a static rule this is, for example, a static rule over here, right? It's quite a famous quote. If it looks like a duck, swims like a duck, and quacks like a duck, then it probably is a duck, right? So over here we have these multiple conditions, right? And we also have the result. So a rule is very, very interpretable. And it's also quite easy to explain to other people as well. If we would change one of the conditions, then and the outcome, it would not be a duck. So if it doesn't look like a duck, then it is not a duck, right? So kind of rules are very explainable and very easy to actually explain to other people. Why actually look at other aspects such as machine learning? Well, rules have some problems. One of the problems is that they're not really scalable. So Wise is an international business, right? Which means that we are operating in different jurisdictions, different regions of the world. All of them have different types of risks and different ways that people behave, or the different ways that people send money, right? So we would need a lot of different rules for these different environments. The other, and with scale, it also means that it's hard to manage and hard to actually keep each of the rules up to date and looking at the latest risks that we might have. So this also means that rules are not dynamic, right? Our machine learning models are constantly looking at how our customers' behavior changes and how the risk that we see in our customers actually changes as well. And we can take all of that into consideration to really have the latest in risk mitigation. So if we're talking about glass box versus black box models, we need to define what they actually are, right? If we look at a glass box model, this is a model where we can follow the internal logic. So we have some inputs. We know what's happening inside to actually get the outputs as well. So an example of this is a decision tree, right? If you look at this decision tree, it's very, very easy to understand what is going on over here, right? Something as feathers and can fly, then based on this tree, it's obviously a hawk, right? However, if we have a black box model, then we only really observe inputs that we give into it and the outputs. We don't know what's really going on inside, right? So an example of this can be a convolutional neural network. And in these cases, we really have to use some external methods to see into the model and get some interpretability and why it actually decided on the output that it did. Right. So when we are talking about the interpretability of different controls, including machine learning, we can almost always draw this little plot, right? So in the x-axis, we can see performance, and the y-axis, we have interpretability. Now, what usually happens is that as you improve on performance and you get more and more highly performing models, they also increase in complexity, and the interpretability aspect of them kind of reduces. So at some point of time, what happens is that you will go from the glass box domain to the black box domain, and different people can decide to draw the line at different areas, but I'd say that a very, very basic random forest algorithm is still a glass box model, right? And any other technology or algorithm that you use, you can really put over here. You can put it on this graph. So rules, as we saw, are very, very interpretable, but they have bad performance. They're hard to maintain, but also they are very black and white. So in the sense that you have some rules, maybe look at volumes or transcript, plus some other aspects. If maybe, in fact, they send a bit less money than the rule flags as suspicious, then maybe we would actually not get an alert, right? Which is obviously something that we are trying to avoid. So this is where models are pretty good. And theoretically, if we look at decision trees, then they are interpretable as well, right? So this decision tree, we can interpret the nice little narrative, right? It has feathers and it cannot fly, thus it is a penguin, right? Very, very nicely explained, and we have this nice narrative, as Luca mentioned before as well. But it's not always really practical, even if it's theoretically possible. Meelis touched upon this shortly as well. For example, we have a tree with 100 nodes, right? So we have maybe 100 plus features, so on. The narrative from it would actually be something like this, probably even longer than what I am showing currently, right? But this is practically not feasible. It is not possible to really follow it. It takes a long time to follow it, and it's something that Meelis touched upon. It's not really explainable, right? It's interpretable, but it's not meaningfully and easily explainable to the end consumer. So you need to use some technology or techniques over here to actually make it easier to explain to other people. And if you're talking about interpreting black boxes, there's mainly two different very popular approaches. The first is Shapley, where we are calculating how to fairly distribute the outcome to different features. So Meelis touched upon this, and also Lime, which also Meelis explained on. But if you're looking at these two aspects, then what Shapley really has as an advantage over Lime is that Shapley has a very strong and thorough theory behind it, which is something that Lime really doesn't have in that sense. And I'll give you kind of a high level understanding of how Shapley works as well. So Meelis showed the formula, but unless you're able to follow it very quickly, then it might be a bit difficult to understand. So let's say you're trying to predict the price of an apartment, right? And we have three different features. We have, is the park nearby? Yes, no. The floor area, so continuous feature, and are cats allowed? Yes, no. And with these three features and their values, we get a prediction that it's actually worth 310,000 euros. But let's say we're trying to find the contribution of the cats allowed feature to the prediction, right? So what we can do is we can fix the other features and we rerun, we send them as inputs back into the model, but this time we randomly sample the cats allowed value from our feature set. In this case, it was no. And the prediction in this case was 300,000. So if we look at this, allowing cats in your apartment increases the apartment value by 10,000 euros. We have the feature contribution over here, right? But would you really bet anything on this feature contribution being accurate? Not really, right? Because we only looked at it in these fixed feature values. So actually what we need to do is we need to run, if we want to find out the cats allowed kind of feature contribution, we need to run it through by also fixing and randomly sampling the values for all of the different features as well, and kind of run through all of the different possible combinations or collisions that we might have. So as an example, if we randomly draw the park nearby feature value, it's no, but we still fixed floor area, then we can see that, okay, in this case, allowing cats increases your apartment price by 20,000. And then we take the average of these two contributions and we get 15,000, right? So on average, allowing cats in your apartment increases the value by 15,000. Of course, we need to do this for all of the different features in order to get feature contributions for all of them. And we actually need to do a lot more samples. So ideally, all of the different combinations have to be scored through. This has an issue. So if you're talking about that we are scoring, for example, at WISE, tens of, if not hundreds of millions of transfers per day, then you have an issue that it's not really computationally efficient to actually look at all of them, right? So to do a full Shapley values run for all transfers as well. So what you can do is you can do essentially Monte Carlo sampling to get a good enough estimation on the feature contributions for each local for each prediction, right? So in conclusion, Shapley values give you the marginal feature contribution for each feature. We have to average contributions over all possible collisions or combinations. And Monte Carlo sampling is something that helps keep it efficient as well when it comes to computational cost. So if you remember, we looked at this performance versus interpretability graph, right? However, recently what has been also shared from 2012 is something called explainable boosting machine, which promises the interpretability of decision trees, but the performance of XGBoost, or comparable performance to XGBoost, which is actually a pretty big deal because XGBoost really does have very good performance, usually. Personally, there's something that I haven't looked into yet. It's in my to-do, but it is something to think about for you as well. And their paper is interpretable ML. So you can find the article freely available online as well. So finally, the final aspect is actually how to present it to end consumers. So the explainability area and how to make it meaningful and easy to understand. And in that sense, we can think about three different user groups, right? We have the data scientists, so these are the most technical people. They are the ones who are actually constantly working with machine learning, with the features, so they really understand the technical aspect of it. Then you have other functions that work closely with data scientists. These might be product managers, operational agents, really people who are close to the team. And finally, we can have external consumers, so auditors, regulators, some different compliance officers. And really, the level of explainability, it really has to be a bit different for each of them. Because as you get further from data scientists, the way you interpret machine learning has to be kind of more easily understandable by the people themselves. So without your input or you teaching them how to actually read the results. And we can look at this as a kind of evolution, right? So in this case, I've taken the feature contributions for the different apartment examples that we had before. Is the park near or is it far? I've added in some additional features here as well, like garage size, number of rooms, and so on. But in the real world, these might be hundreds of features, right? So having it in the database is pretty good. Is it usable? Not really, unless you do some additional filtering on it. So something that we saw from Luca's slide is that we can actually show the most impactful features and their values for each prediction, right? So what pushed the score up, what pushed the score down? In this case, it was an example of bike rentals, depending on weather and stuff like that, right? And what you can actually do over here as well is that rather than showing off the hundreds of features, you really only show the top that push it up and top to push it down. So you filter out all the middle ones that have really minimal contributions to final outcome. Because at the end of the day, they're not really that important. And kind of the gold standard is this narrative, this human readable text. It has feathers and cannot fly, thus it is a penguin. So this is, by default, this is already understandable to everybody. You do not need to know anything about any of these kind of features, about what's pushing the score down, what's pushing the score up. Need to understand anything about any kind of threshold, stuff like that. It's just a nice human readable text and easily understandable. And this is kind of the gold standard, I would say, in some sense. So if you can show this, and at the same time, you actually have the raw data as well, then you're in a very, very good place. But actually get over here with complex and advanced models is quite a large challenge. So thank you for your time, and I will now take your questions.
Thank you very much, Ryan. So let me check about the questions. I actually think that the next questions that came up can be addressed to the whole panel board. So maybe we'll switch to the panel discussion, and we'll try to address the following questions altogether. Okay, great. Thank you very much. So I've had a question. Perhaps it's mainly for Ryan, since his presentation was the last, but to all the rest of the speakers as well. And my question concerns the privacy problem. So for example, we have a data set, and for some reason, some features or all of the features actually were obscured in this data set. So names were hidden, features renormalized, so some of them combined, stuff like that. So is there a way to build an interpretable system using these kind of features? Or do you have any experience with that problem? So yeah, probably Ryan, you can comment on that.
Yes. So when we've anonymized features, essentially, right?
Mm-hmm.
Yeah. So this is something that so far we do quite a lot in Wise as well. It also handles the aspect that if somebody sees the features, right, then they would not be able to actually know who the user is that the features are about. So I would say in that aspect, since we follow the methodology that Luca brought up before, in that we are taking our features actually from working very closely with the operational team, our features by design really are interpretable, right? There are features that might be harder to understand in the sense maybe we're looking at some ratios or some more difficult aspects. But what you can always do is that you can always, in the tool, you can also always leave a tooltip that kind of very shortly tells you what the feature is actually about. So we really use interpretable features in our current model setup.
Okay, thank you very much. Probably, Radwa, I see you are muted, so probably you have a comment.
Sorry, I'm not.
Yeah, I just saw that you are muted, so
No,
I
no.
thought that you have a comment on that.
Maybe to add to what Ryan said, and I think what you were referring more was like, how do we ensure that you know, there is that there is no privacy concerns, right, among the features that we have and we use in the models. I think we have very strong privacy team, and so we collaborate with them to make sure that that's the case, right? And so obviously there is laws and legislation that we need to follow and make sure that we obey to those. Also from a perspective of where the training sets sits and or sort of where they are stored and who has access. All of this is sort of very nicely compartmentalized, so that actually there is only specific groups that have access to certain data sets, and this is of course not shared unless you are in that group. So in that way you mitigate also these risks as well.
Okay, thank you very much. We have also a new question popped up in the chat from Novin. Question is to all of the panelists. So hypothetically, if we have an amalgam of a neural language model conjunctly trained with the model that is specialized in a specific domain, say, for example, fraud detection, and this amalgam model produces an explanation in a natural language format to explain the output of a specialized part. Would this be considered an interpretable or explainable model when we have such jointly trained system? And how does this approach stand across the explainable aspect?
So maybe I could start.
Yes, sure.
So, I mean, basically rephrasing it, we're talking here about a model that not only produces prediction, but also the model itself produces an explanation. And so how does it stand in the zoo of different explainable AI methods? I would, so first of all, it definitely produces an explanation, yes, but another question is how can we trust it? So because it's the model itself, and if it's neural, so it's a neural network that produces this explanation, is it possible that it kind of is not the same same explanation that actually the prediction part uses? So what ensures that that the prediction part and the explanation part are talking about the same thing and using the same features the same way? So yeah, it's something that maybe needs further guarantees. And when talking about guarantees, this is something that in machine learning is in its infancy. It's really very little that machine learning methods can guarantee at all. I think there are definitely these complex models that work together with different modalities. For example, create an image, create some kind of text with it.
Like clip model, right?
Yes, and then these nicely often go together. But what if sometimes they don't? So can we still trust them? So the errors can still happen. So maybe there is a need for still some kind of governance, of some oversight about what is going on, explanation about how the explanation was obtained. So it's not clearly a lot of research to be done still.
Okay, cool. Perhaps a follow-up question to Radwa. Maybe you've tried to like use something like Clip to generate concepts from the textual description?
Still, we actually first started to apply the technique on tabular data first, but we're still in very early stages. But for text, it's still also very hard to come with concepts, like still in very early stages.
Okay, and do you use a lot of natural language processing in Wise, Ryan, Luca?
Yeah, we do in sort of other domains, like there is a whole customer support sort of we call them tribes, right? So where sort of NLP has been used, and there is a continuing sort of development. So. So yes, we have used it. Maybe we should use it more within the Fincrime domain as well, actually. So there is opportunity there as well that hasn't been explored well enough. Yeah, essentially yes, but much more could be done.
Okay, thank you. I also have a question considering one of the points that Meelis has raised in his presentation. So Meelis, you've talked about the responsibility of different, call them stakeholders for the machine learning algorithm decision. So I guess broadly speaking, the question is who to blame? Who is to blame for machine learning model decisions? So for example, we have, I know, the end user, the developer, the provider of the service, and how this like blame arrow shifts depending on how explainable the model is. So what do you think? So who is responsible for the end decision?
Yes, I mean, this question of responsibility is also one thing that holds back the whole of autonomous transportation, because we haven't solved this problem, like whom to blame and how to ensure that errors don't happen. With medical domain, it's clearly that the doctors currently are responsible. I don't know whether it would change at some day, but basically, if we want the AI systems to take more responsibility to solve tasks that are harder and harder, they eventually the responsibility needs to go to well, we can't really put the AI system to jail, so it probably needs to be then the developer company or someone from there who actually needs to be responsible. But the legislation is not there to make this happen, I think.
Okay, and how are things currently in Fincrime? So is the system just an, I don't know, alert assistant to a human at the moment?
Yeah, I mean, sort of so the important things to emphasize is that at the moment we want the models to have good performance, so that actually anything that it is alert will ultimately have a human decision, right? So there there isn't a case where sort of the machine or the system takes the decision of its own. So I think that sort of avoids a lot of problems, and makes sure that ultimately the right decision. That we also sort of try to keep the two things separate, right? So that actually the humans that review the case that has been flagged take that decision on their own, just based on their own knowledge, rather than actually being sort of biased by certain model decisions. So yeah, so I think that for us, we are still a little bit far away before we can confidently use the system to decide from A to B. And but who knows? Hopefully, Radwa and Meelis will help us to build such a system.
There will always actually be a human in the loop. There must be. We cannot take it completely.
Yes, I agree.
It's just a tool that can assist us to take better decision, but assist us. But still, we are going to rely on people to take the decisions, not the models completely.
Yeah, because at the end of the day, right, if we have low risk opportunities, then maybe there, yes, we can use models to do automatic decisions, right? But if we have this kind of high risk or highly regulated areas, so let's say medicine, right? If we have a model that is automatically looking at the radiological data, so an image of your X-ray, for example, what you'd rather want it to do is you'd rather want the model to be risk averse, so it rather forwards something to the doctor for further review, rather than it having a false negative. So you want the doctor to review it, even if it's a false positive, because maybe there is cancer there, maybe there's not. A human life might depend on it, right? But you don't really want the model to kind of automatically say that there cannot be anything over there.
Just to add a bit, when someone builds a breach and then this breach collapses, it's really kind of the engineers that are to be blamed, and if it's clear that some engineer has made a mistake, it could be leading to prosecution, right? Currently, AI is not yet an engineering discipline in that sense, that we are yet in the process of kind of trying things and hoping they would work, and there are really no guarantees. We cannot compute and prove that everything will work fine. We just hope that it works fine. So in a way, it's not that different from how humans work. Humans also make mistakes, and maybe it's even inevitable. Maybe machine learning can never become such that we can fully perfectly trust it. And it will make errors, maybe we just need to live with it, but currently there is the question of responsibility, so that's overall.
Yeah, some good news, we won't lose all of the jobs to AI as of yet. Okay, and perhaps lastly, I would like to discuss a topic of the data, and in particular data collection. So some of it was mentioned by Luca in this pipeline chart, how to collect the data. So do you think we need to change something in the data collection procedure to make the models more interpretable? So in short, is there a way to approach the problem of explainability and interpretability from the data side? So probably we need to change something in rotation or things like that.
Sorry, was it asked to me?
Yeah, perhaps you could comment. So how the annotation process is going?
Yeah, that's a good question, actually. From well, in some sense, I touched to that. Like for me, is it comes a lot. It comes down a lot to what you input to the models and how you came to that decision of having a specific feature in the models. For me, like I don't really particularly a big fan of finding all sorts of features that in there that you don't know where they come from. Like I don't know. Like for example, you could include temperature in a fraud model and see if it correlates with fraud loss or with the fraud sort of labels. So like it's just like it doesn't make very much sense. Like I really want to have a very well explained logic of why a feature is there and represents specific behavior. In that way, you kind of solve a little bit of the problem afterwards in how you give an explanation of the model output. So that's what you can do at collection sort of time.
Yeah, so we should also always keep in mind how are we going to interpret this feature if it turned out to be useful, right?
I think so, yes.
Okay.
Yeah,
And
this is my sort of like, this is really what I believe a lot, actually. Yeah. It actually avoids you a lot of problems with whoever asks about the model. Sorry, Ryan, please.
Yeah, and to further talk about a bit, the pipelines or the data graphs and how you actually collect the data, those have to be maintained and kept up to date as well, right? So that you don't have any kind of data lag, or that actually maybe a year ago you built the data pipeline where you're gathering one feature, but maybe some underlying sources or the business logic somewhere has changed a bit. So maybe you have some feature shift over here. So this is something that you have to monitor as well, that actually the features that you are gathering and what you're expecting from your features are actually the ones that you have, and at the end of the day that you are further forwarding to the model as well. So this is where things such as feature monitoring come into play.
Okay. Meelis, Radwa, any comments on this topic? Just to finalize the discussion.
I'd just like to emphasize that this approach taken at WISE with trying to come up with already interpretable features is really useful. If that's what you can do with your data, that sounds really good.
Also, it's related to the topic of concept interpretability. Maybe the features by themselves are not meaningful, but maybe if they are combined in a specific way, maybe they can create a meaning, and it will be actually easy to explain and provide useful explanation for users.
Okay, that's great. Thank you very much. Big thanks to all of the speakers and to everyone in the audience for joining and for great questions. I'm really sorry to all the people whose questions we were not able to answer due to the time limitation, but of course you're very welcome. I think you're very welcome to reach out to the presenters. Yeah. Unfortunately, we're already out of time. So thanks again for joining. And recording of this webinar will be available soon in the social networks of University of Tartu. So keep an eye on them, subscribe, share. And yeah, thanks again. And hope to see you next time on the next data science seminar.